Yeah, so my project is about text algorithms and new trends in text algorithms. Let me first. Trying to figure out how to change the slides here. Okay, can you see it now? New slide? Okay, thank you, sorry. So let me start with old trends in text algorithms, or just classical text algorithms. In the classical text algorithms that some of you might have seen at the course that we have at the university, deal with the Knuth-Morris-Pratt algorithm as shown here, or maybe the suffix tree as drawn in this example. And also there is some part related to combinatorics on words as presented here. So periodicity lemma and this kind of stuff with string periods and string properties. And these are the classical tools of string algorithms that we are somehow based on, but we go beyond what is known here. And let me show you an example of a problem that we could deal with. In the example problem, the very well-known one, we are given two strings, and you want to compute the longest substring, so the longest fragment of one string that occurs also in the second string. This is a very well-known problem. The solution was invented almost 50 years ago. Even though at that time it was quite revolutionary, and Donald Knuth called it the algorithm of the year when he saw the solution, because he thought that there would be no solution beyond n log n time for this problem. But then the solution using suffix trees was the breakthrough in this area. However, well, this was a breakthrough 50 years ago. Right now it's a classical result. We also teach this algorithm at the Algorithms and Data Structures course at the faculty, so it is very well known right now. But then things start to becoming more complicated when we consider variants of this very well-known problem. And let me just show you some new trends, some new variants of this problem. One of them is dynamic longest common substring. In this version, okay, we have those two strings and their longest common substring, but then we can make some changes in the strings. For example, we can make a substitution in the first string, changing the letter C to the letter A. And then it turns out that the longest common substring becomes a bit longer, and it is located at quite a different location in both of the strings. So this starts to becoming more interesting. And it turns out that for this problem, it was only 2 years ago when we invented an algorithm that was the first one beyond the naive linear time algorithm, which would just recompute the longest common substring after each substitution. So this is one example of a direction that one can go from this problem. Another example is approximate longest common substring. This one is much motivated by practical applications in which you want to know how much the two strings are similar, but you can allow for some small number k of errors. So here, for example, you have two strings, and the approximate longest common substring with just one mismatch has length 7, because we have these two strings and they have just only one small mismatch, but other than that they match completely. And then you might be asking, what is given this number k, what is the longest approximate longest common substring of two strings? And then it turns out that for this problem, well, first of all, a solution working n times log to the kn time was known before, but the question is, can one do better? And we showed this year that, well, okay, we shaved the first square root of log n here in this algorithm. However, like we hope to try to know whether we can really beat this log to the kn substantially or not. There are some intuitions why this could be not maybe possible, but it's not clear at this point. And on the other hand, we have shown that for a general k, you cannot solve this problem faster than the naive quadratic time algorithm. But there is to approximation which works in beyond n squared time. So this is another kind of a non-standard variation of the problem, which is practically relevant, and still there are some new results, but there are as well open problems in this area, and it's not totally clear what are the answers here. For example, can you beat this log to the kn or not? Or how far can you beat it? Yet another direction is packed longest common substring, because in stringology you often consider the case when the input is very large, and then you want to try to pack this input into bits. So for example, for a constant size alphabet, you can pack up to log n characters into a single machine word, and then the strings have actually length not n, but n log sigma divided by log n, where sigma is the size of the alphabet. So then in this case, so this is the actual size of the input, and this is often the case in applications of text algorithms, for example, bioinformatics. And then one could ask whether, given such a representation of two strings, a packed one, can you compute the longest common substring faster than the linear time solution, because the input size is now smaller than linear, actually. And again, we have shown very recently that you can do, well, the ideal would be to shave the complete log n, but we managed to shave a root of log n, and using some well-known conjectures, there's a high chance that this is an optimum that you can achieve here, but still there is no proof for that. So again, this is a step towards this goal. And in many other problems from text algorithms, recently there were results like that presented for text indexing or longest common extension queries. So this is an active direction where you can try to work and study text algorithms from a completely different but very practical perspective. And there are many other variants. I haven't mentioned all of them to you, but the streaming model is still quite active in text algorithms, and some non-standard equivalence models are also actively studied. There are some variants where you study predictor-friendly implementations of simple algorithms. So there's a lot of stuff going on, which like studies the same classical problems, but asking new questions or trying to go deeper in the understanding, not just the standard classical model, but then like the real world applications. And this is the majority of things that we are working on. We are also working on some combinatoric stuff. Here is an example of a well-known classical problem, in which you want to ask how many different square substrings are there in a word, where a square substring is just a substring, so a fragment composed of two equal strings, like 0, 0, or 0, 1, 0, 1, or 1, 0, 1, 0, and so on and so forth. So here, for example, for this input, the output is 5, because we have 5 distinct square substrings, so you're not counting the same substring multiple times. And it is known that the maximum number of such substrings in a word of length n is, well, it can be almost linear, and the upper bound is a bit less than 2n, but still those bounds do not meet. And like the first result in this area were more than 20 years ago, and still the exact answer is not known. We don't have an answer for this yet. But, for example, we have been studying the two-dimensional case in which you consider as a square like 4 copies of the same string, and we have shown that in this two-dimensional case there is a bound n log square n for the number of distinct 2D squares of this form in a 2D string, and like again, this was better than the previously known bounds, but still it doesn't give the exact answer here, even from the asymptotical point of view. So this is another direction which we are studying in our team. And well, maybe I should have started with this in the very beginning. So this is the team in which we are working. So there's Professor Ritter, Tomek Waleń, and Julek and Victor, who are PhD students, and they are just finishing their PhD right now. We have been working with several master students, and we are actively collaborating with people from abroad, which is not a surprise, taking into consideration all the previous presentations. And we are also looking for one more PhD student for starting from this year. So I should have mentioned some particular open problems. However, in most of the results that I have shown, they are still not the asymptotically optimal ones. So, for example, the problems that I have presented here, there are still open questions remaining, and there are other problems of a similar kind that we are trying to tackle right now, and we want to tackle in the future. And there's a lot of space for new projects for PhD students. Okay, thank you.
Maybe if there are no questions, you could describe somehow, like from all these topics that you were mentioning, what would you foresee as a prospective specific topic for a PhD student? Which one of these you would find more exciting to?
Well, it really depends. It really depends on the profile. For example, in our team, there are people who are mostly interested in the combinatorics part, for example, and they are really keen to know what is the exact complexity, for example, here on the number of squares. And these kinds of problems you can attack both using some combinatorics tools and also using machine learning tools to try to find the best examples and then generalize them. So this is also, in some sense, an experimental area. So this would be one of the topics. But right now, if you are mostly interested in algorithms part, well, I think that, for example, this problem where you want to really know how far can you go beyond in this problem and in similar problems of the approximations, I think that this would be maybe the most interesting. It's challenging, but this kind of analysis is currently taking place in the text indexing problem, and there is some very weak conditional lower bound for the number of for text indexing with mismatches, which is n to log to some function of kn in a very strange model of computation. So, and it still was an interesting result to show. So if someone is interested, for example, in conditional lower bounds, then this is yet another interesting direction to work. If someone is interested in improving the complexities of algorithms using, for example, the suffix tree and its optimizations, then trying to shave this log as far as we can and show what is possible, how far can you go beyond in this problem. This is also some direction. So it really depends on the profile of a student. So
fantastic. Thank you very much.